All right, guys. So here we are, kind of wrapping it up with our last few topics for the semester. And one of the standards that was set out when they created this course for Chemistry 2 at James Clemens was to spend a little bit of time talking about nuclear chemistry. And so essentially, kind of in a nutshell, that's when you make changes to the nucleus of an atom, and energy is typically released as a result. And so what we're going to do is kind of just give you a brief overview of kind of what nuclear chemistry is, how it can be used, and then kind of take a look at the three main types of nuclear reactions. And so I wanted to show you all a site kind of right quick. It's under this question. It says, what is a nuclear chemist, and what do they do? And so there's a really neat site provided by the American Chemical Society called College to Career. Actually, I think it's like a part, of their main website. But what they do is they give information about tons and tons and tons of chemistry applicable, careers that you could take your chemistry and use to, actually kind of have a job with or something. And so you find things there that you're like, wow, I didn't even know those careers existed. Like, here's just a little list over here: chemical technology. You could work in dyes, pigments, and inks. There's textile chemistry, water chemistry, astrochemistry, lab management, health and safety, oil and petroleum, paints that require some chemistry. Public health. And so just lots of stuff. And so if you're ever interested, like, hey, I like chemistry, what might I be able to do with this? They have a lot of good resources there. And so again, that's American Chemical Society, their College to Career. And they also have kind of within that, like for every field, they have like a sample profile, like of an actual chemist who kind of works, within that field. So that's neat as well. All right, so now that I've told you that, let's look specifically at kind of this overview of what a nuclear chemist does. And this kind of helps you get a better feel for how this stuff is applied. And so it starts off talking about, radioactivity and how that often comes up in, superhero movies and kind of, different things. But essentially what your nuclear chemists are typically doing is they're looking at different isotopic forms. And so that isotopic comes from the root word isotope. And so you're looking at different forms of the same element that have different mass numbers. And you're looking at what's called fission and fusion processes, all right? Or sometimes you're looking at the effect that radiation might have, if people or animals are exposed to it. And so they may work in labs, doing more hands-on stuff, or their work may be more theoretical, which is more like thought, pencil and paper, different things like that. And so there are different places they can work: private industry, like nuclear power plants. When you have like cancer centers using radiation as treatment, kind of the development for that, they could be a part of different things like that. Or a lot of today's medical imaging, like different tests that you may have run to, trace certain things or, find out if something is wrong. That requires oftentimes or uses, radioactive isotopes as tracers. And so they can be involved in a lot of the research, developing different nuclear power sources. Like it says here, developing medical imaging and therapeutic treatments using radioactive materials. Or it says kind of on the flip side, if people have been exposed to kind of too much radiation, they can work to try to develop different treatments, for those injuries or for those different illnesses that can come about. And so it's just kind of interesting, you're welcome to pop on and keep reading, like, what education it requires, like what their workspace may look like. Here's kind of a picture of some medical imaging. And then at the bottom, they typically have a thing like, hey, is this going to be a good fit for you? So that just kind of gives you an idea, of what we're talking about here. And typically, so far in chemistry, what we've been used to talking about are just kind of plain old chemical reactions, which are incredible in their own right. But most of the time, in life, in our bodies, what we're more accustomed to seeing occur are actually the chemical reactions. And so here's what sets the chemical reactions apart from the nuclei. So in a chemical reaction, what you're rearranging are the bonds between atoms in a molecule. So for example, if I wanted to change water into hydrogen and oxygen, I'd have to break the bonds within water and make new bonds for just hydrogen and just oxygen, okay? And so chemical reactions, what we're doing is we're changing the arrangement of the atoms. We're breaking the bonds and then rebonding them in a different pattern. Now, nuclear reactions, on the other hand, we're not changing bonds, so to speak, but what we're changing is the nuclear structure within the atom. So in a chemical reaction, you're not changing the identity of the atom. You're not changing its nucleus. You are changing the identity of the molecule, but the atoms overall stay the same. If you start with carbon in one of your reactants, one of your products should also have carbon. But what we're going to see in nuclear reactions is that you may start with one atom as a reactant, and then as a product, you may end up with a completely different, atom. And so that's because we're going to be making changes to the nuclear structure of the atoms. And when their nucleus changes, well, so does the identity of the atom itself. Now, within this kind of class of nuclear reactions, there are three main types. There's fusion, fission, and then radioactive decay. And so in fusion, what we have is you have two small atomic nuclei are going to come together to make one larger nucleus. And here's kind of an example over here. So you have two smaller atomic nuclei coming together to make one larger nucleus. Now in fission, that's going to be the opposite process, where you start with one large atomic nucleus and it will be broken into smaller fragments. Sometimes that may be 2 fragments, sometimes it may be 3, and just kind of depend. So fission is where you're taking one large nucleus and breaking it into more than one, so into smaller atoms. Now, the third type is radioactive decay. And this is where you're starting with an unstable nucleus, and it's going to be changing into a more stable nucleus, okay? And so you can call it unstable, you can call it less stable, but essentially you're starting off with something that's not stable, and it just kind of naturally on its own will decay into something that is more stable. And so to kind of show you what that looks like right quick, at least the unstable part, this may be a simulation that you may have used in Chemistry 1 when you were talking about isotopes. And so just as a reminder, when you have isotopes of an element, that means that the number of protons is the same, but what can vary is the number of neutrons. And so you'll see sometimes when an atom ends up with too many neutrons, that can make it unstable. So you'll see my little lithium atom is kind of shaking now. Or sometimes if it ends up with too few neutrons, that can also make it unstable. If an atom is stable at a given number of neutrons, then that means it's a valid isotope. So for example, lithium-6 and lithium-7 are both stable. However, lithium-8 and lithium-5, are both unstable. So those isotopes don't exist naturally. So if I had something, say for example, like lithium-8 that was unstable, it's going to want to decay and, change its nucleus so that it becomes stable. All right, let's get back to our notes here. Okay, and so when we're going to kind of talk about these, we're going to kind of group fusion and fission together. And then radioactive decay is a little bit more of its own thing. Now, radioactive decay and fission are related in that when you start with one unstable atom, it decays into other things. But they don't always, line up one for one in how they work. And so, for example, fusion and fission, they both require kind of high energy to make them occur, or just kind of a really heavy mass of heavy radioactive elements. Now, radioactive decay, on the other hand, doesn't have to be forced as much. It automatically happens anytime you have unstable nuclei. So we might ask, okay, well, what causes, unstable nuclei? And that's what we just looked at in the simulation, is that whenever you have too many or too few neutrons in your atom, or your nuclei are just kind of too large to really be stable. And so here's an example of a uranium atom, which is really large, and you'll notice that a lot of this radioactive decay oftentimes will involve elements within the F block, kind of that little strip of elements beneath the periodic table. So uranium is one of them, and so here we see it decaying to a thorium atom and releasing what's called an alpha particle of radiation. And the reason it's called radioactive decay is because when these unstable atoms change into a more stable atom, they tend to give off some type of radiation. Now for us, we're going to talk about kind of the three main types of radiation. We've got alpha particles, beta particles, and gamma rays. And you've probably heard about them, these terms just kind of mentioned, but we're going to look a little more in depth at what they actually mean. So an alpha particle is essentially a helium nucleus, all right? And so anytime you see either this little Greek alpha symbol or a helium nucleus, that's representing this type of radiation known as alpha decay. And so its charge is +2, it has a mass number of 4, and as far as how penetrating or how dangerous this type of radiation is, it's very minimal. It typically will not penetrate skin, and it can be stopped with even a sheet of paper. And so here's kind of an example of what we call a nuclear equation. So here what we're showing is uranium naturally decaying to a thorium atom and releasing an alpha particle of radiation. So this is the equation behind the process that we looked at earlier in the picture. Now a beta particle, on the other hand, is actually very similar to an electron. And so what it is, or not very similar to, is an electron, I guess I should say. And so the symbol for a beta particle is kind of this Greek B here. And then its symbol, kind of in the nuclear equation, is a 0 for the mass number, a -1 for its charge, and then the little e to remind us that it's an electron. Now, as far as a beta particle's penetrating power, its penetrating power is more than an alpha particle, but less than a gamma particle. And so it will penetrate skin and some tissues. And some skin tissues is what, or like internal tissues is what we're talking about. And then finally, gamma rays, that's a form of electromagnetic radiation, a form that's very high energy, kind of way on the high energy end of the spectrum. It doesn't have a charge, it doesn't have mass, and so its symbol is just the little kind of Greek Y there. And its penetrating power is very deep. And to kind of show you this graphic right quick, Compound Chem, here we go. This kind of shows you this little graphic in the middle, like how much they penetrate. So you see the alpha particles are stopped by paper, beta particles are stopped by aluminum, and then gamma particles, you have to have something much stronger. And so the fact that, radiation can be damaging is why, like, anytime that you're getting an, x-ray, maybe at the dentist, they'll have you wear a lead vest to help protect, like, your organs and different things, from the radiation. People that work in, like, x-ray labs and different things have to be very careful, about their exposure. But there are, other good uses of radiation as well. For example, it talks about some down here, like smoke detectors. Many of them contain americium-241. It releases alpha radiation to actually help detect smoke. Sometimes in pacemakers, you can have different elements that emit alpha radiation to kind of use to power, people's pacemakers, to help with their heart. For beta radiation, those are some of the things you can use in medicine as chemical tracers in the body. They've sometimes been used in cancer treatments, and this is one that I find really cool, is that they can also be used kind of as a tracer, not only in our bodies, but also to help find leaks in, big underground pipe systems. And they can also kind of be shot at materials while they're being manufactured to kind of help, quality control the different thicknesses. And then finally, gamma radiation. This is really interesting here. It can be used, since it's so powerful, so high energy, to kind of sterilize medical equipment, sterilize packaged foods, and, killing off different bacteria and, other things that you don't really want. And it's also used by telescopes to kind of produce images as well. And so just kind of interesting that, they can be harmful, but you can also use them for good, if used properly with the right sorts of protection. All right. And so then again, here are kind of how they appear in a nuclear equation. So here we have a carbon-14 atom kind of decaying to a nitrogen atom. And then here is your beta radiation particle. And then here you have technetium, and this is a gamma radiation particle that's being released. All right. And so these nuclear equations are kind of what we're going to end off with by practicing. But right quick, while we were talking about, some of the uses, I thought it's maybe interesting to look at some of these that may hit, kind of close to home. One of those, thus being in North Alabama, is TVA, which is called the Tennessee Valley Authority. And they are the ones kind of responsible for the different nuclear power plants kind of in this area that help produce some of our power for us to be able to, do this e-learning on our computers, for us to, turn on the lights in our house and just different things like that. I actually worship with, I guess, two people who work there. One is a chemical engineer, and the other one kind of works on more of the kind of physics side, but, helping with the nuclear reactors and different things like that. And so these nuclear reaction processes can be used, to help generate energy, for us to use in our lives. And then also radiation therapy for cancer. Many of us may have family members that have, or, friends that have been affected by cancer. And so when you hear about them sometimes being, prescribed radiation therapy, that's something where, this comes into play. And so just wanted to kind of read you this right quick. This is from cancer.gov, and it says how radiation therapy works against cancer. It says at high doses, radiation therapy kills cancer cells or slows their growth by damaging their DNA. Cancer cells whose DNA is damaged beyond repair stop dividing or die. When the damaged cells die, they are broken down and removed by the body. Radiation therapy does not kill cancer cells right away. It takes days or weeks of treatment before DNA is damaged enough for cancer cells to die. Then cancer cells keep dying for weeks or months after radiation therapy ends. And so kind of the type of radiation therapy that's used, depends on like the tumor, exactly where they're trying to target. But essentially what it does is that, high energy radiation damages those cancer cells' DNA and kind of stops, damages it to the point where they aren't able to reproduce. And so, again, that kind of illustrates the point that, radiation, that's how it can be harmful, to people, is by damaging, DNA, damaging your tissues. But they've also found a way to kind of, use it for a good application. But as we know, radiation often has many side effects that kind of come along with it too. And so, all of these things kind of, just tie in together. I thought it was interesting to kind of show you where some of this can come into play. And so typically, another application that's oftentimes talked about anytime like radioactive decay or nuclear chemistry are taught is the idea of carbon-14 dating. And actually, that was the equation listed underneath the beta decay category. And what happens is you have a carbon-14 isotope that over time will naturally decay to a nitrogen-14 isotope, and it releases, beta radiation in the process. And so typically, I know at least for me, kind of high school, college or whatever, when this topic was taught, it was often presented kind of with the idea of supporting the Earth being several thousand or several, maybe even millions of years old. And so I did kind of just some personal, research and reading on that at the time. I wanted to make sure, I knew what I believed, make sure, I understood the process. And so I'm going to introduce you to a phrase that I think is really helpful to keep in mind, especially since, you guys are interested in science. Some of you may end up going into fields, that involve that. But there's a phrase I think is important to understand, and that phrase is called the limit of effectiveness. Get that out there. So the limit of effectiveness, or kind of another way to word that, might be the scope of measurability. Measurability, there we go. All right. And so what these two ideas refer to is that in science, different, techniques, different ideas, processes are typically limited to a certain, range of effectiveness, or they're limited as to, the range of data that they can actually measure. And so for carbon-14 dating, it's, another one of these techniques. And like many techniques, there are certain conditions that have to be met before carbon-14 dating is actually, effective, or before it generates, actual real kind of usable, valid data. And so, I kind of started looking into that and, found that oftentimes when, I hear some of those dates, generated, those like precursors or those requirements for carbon-14 dating to be effective are often not present, such as knowing the amount of carbon-14, in the atmosphere, did the decay rate stay constant, different things like that. And it's interesting, as I found, just kind of looking around, even those who will support, the idea of, the Earth being several millions of years old, one of those individuals who's very, kind of prominent within that idea is named Richard Dawkins. You may have heard of him. He's written several different books and things. But it's interesting, I kind of found this quote that even though he supports that idea, he's very honest as far as admitting, as far as communicating, the scope of measurability or the limit of effectiveness of carbon-14 dating. I'm just going to read you this quote right quick. And he said in one of his books, page 226, it says, so he said, different kinds of radioactive decay-based geological stopwatches run at different rates. The radiocarbon stopwatch buzzes around at a great rate, so fast that after some thousands of years, its spring is almost wound down and the watch is no longer reliable. And here's where he says it a little more clearly. He says, carbon-14, is useful for dating organic material on the archaeological or historical timescale, where we are dealing in just hundreds or a few thousands of years. But it is no good for the evolutionary time scale where we are dealing in millions of years. And so kind of the more you look into it, you see that it's really not, effective at generating, valid data outside of the range, of a few thousands of years, just some of those, requirements and kind of precursors no longer being met, or known. And so I just want to encourage you guys that, anytime you see something that you may say, well, that doesn't, match like, what I believe, to go, and look into it, to research. And, for me, anytime that I've had that happen, where I've, had to dig into something, in science, what I found, just personal experience, I know others who would, say the same thing, is that true science to me has always confirmed, my faith and what I believe, about the earth being created by God in 6 days, him resting on the seventh. My, faith in, him creating me as a person, the animals, different things, in a wonderful way, and our earth being, a lot younger than some reports, might say it to be. And so that's what I want to encourage you to, is when you hear something for the first time, don't be afraid to check into it, because time and time again, I found that things at first that seemed to contradict my faith, when I looked into them. They just really went along with it and supported, the biblical account as well. And so, anyways, so just wanted to point that out. And of course, just from personal perspective, I always want to look at things through the lens, of the Bible first, trusting God as the one who made me, who made everything. And so to, trust him to set the standard first. But like I said, oftentimes when I look at things and try to distinguish, true science and, the proper range of effectiveness, that has just, confirmed and just supported and, falls with kind of everything else that I believe. And so don't let some of those things, shake your faith, but look into them, take God's authority as the first one, the final standard. And then that can, just kind of help you as you go forward, as you encounter kind of different things in life or in your studies in college. And so what we're going to do to practice right quick is we're going to try to write or kind of fill in the blanks rather to some different nuclear equations. And again, these just are illustrating the processes of fission or fusion or the radioactive decay, alpha, beta, gamma radiation. And so what we're going to do is look at this idea of, okay, well, how do we know what type of radiation is emitted, or how do we know, what new nuclei are going to be formed? And so this is going to resort back to what's called nuclear notation, which you would have covered back in Chemistry 1 when you were first learning about the atom. And so just to remind you right quick, so the number on top is what's called the mass number, which is the sum of the protons and neutrons in an atom. And that's what tells you kind of which isotope you're dealing with. Now the number at the bottom, this is the atomic number. That's the number of protons within an atom. And that helps you identify which specific nucleus, which specific atom it is. And so you'll definitely need your periodic table because the atomic numbers are what are going to help us identify the elements. So what we have to make sure happens is that the mass numbers on the left have to equal the sum of the mass numbers on the right, and the atomic numbers on the left have to equal the sum of the atomic numbers on the right. And it's interesting, kind of we're talking about mass and energy and all that stuff. And this section of chemistry is actually where Einstein's kind of famous equation that E equals mc squared, the energy is equal to mass times the speed of light. This kind of falls into that. We're not going to go into it, but it's really interesting, and you're welcome to check that out for sure if you want to. Okay, so enough talking for me. Let's go on with the practice problems. So what we know is that this is an example where we have one nuclei decaying into two. And so first of all, let's go ahead and identify that as fission, where we have one large nuclei breaking up into more than one fragment. And so what we know is that whatever atom that goes here, it has to have a mass and a mass number and atomic number that when added to 192 and 77 respectively will equal up to 231. So what we can do to figure out the mass number of our new element is take 231 and subtract 192. That gives us a number of 39. And so again, 39 plus 192 needs to equal 231. Now to find the atomic number, which will identify the atom, we'll take the bottom number 91 and subtract the other bottom atomic number 77, which gets us 14. So now, this bottom atomic number is the way we identify the atom. So if we go to our periodic table and look for element 14, that would tell us that this is a silicon atom. And so it's decayed to iridium and silicon. All right, so now let's go ahead and do the next one. So here we have helium and hydrogen, and they're coming together to form just one new nucleus. And so this is going to be a fusion process where they're coming together. And so here what we're going to be doing is kind of adding everything up. So 4 plus 2, that gets us 6 for the mass number. 2 plus 1 gets us 3 for the atomic number. If we use the atomic number to identify, lithium has an atomic number of 3, so that will be the new nucleus that's created by this fusion process. Okay? All right. So now what I'm going to have you do is kind of pause the video right quick and try 10, 11, and 12. fission or fusion processes. The last page of the notes is an answer key where you can check yourself. Then if you'll pop back onto the video, we'll work just a few of the nuclear decay problems, and then you can finish those up. All right, welcome back. Or maybe just thanks for hanging in there. If you're still watching and didn't go try the practice problems yet, but try them, really do. All right, so anyways, so nuclear decay. So this is the one where we're talking about kind of the alpha, beta, gamma radiation. And so these first few problems just ask us to name the type of nuclear decay. And so if we scroll back up to our little chart here, so for alpha radiation, what you're looking for is a helium nucleus. For beta radiation, that's going to be an electron, 0, -1. And for gamma rays, that's just going to be a gamma symbol. And it'll often have 0 and 0 beside it because it has no charge and also no mass. Okie doke. So here in this first one, we have kind of our beta radiation symbol. And so we'll go ahead and label this as beta decay. For number 2, we have the helium nucleus, which is equivalent to an alpha particle. We have the same thing on number 3, so this will be our alpha decay. And then finally, on number 4, we have both beta and gamma decay occurring at the same time. All right, so now for the rest of the problems, it's going to give us a blank to fill in and then ask us the same thing to identify the type of decay. And so on number 5, it's got a helium nucleus, which is going to be alpha decay. And then just like before, we want the numbers on top on each side to equal and the numbers on bottom on each side to equal. So we know that whatever is going to add to this 4 has to add up to be equal to 226. So 222 plus 4 will be equal to 226. And then 2 plus 86 will be equal to 88. And so if we look on our periodic table and look for element 86, that's going to tell us that we have radon, which has a symbol of Rn. All right, now let's do number 6 right quick with some beta decay. Now on this one, if you'll notice, this is a -1. And so what that means is that whatever the bottom number here is, that when you add it to -1, it has to be equal to 19. So what that means is if we take 20 and add a -1, that's like subtracting. So 20 minus 1 is 19. And then here, the 0 doesn't take away from anything, so our top number is still going to be 37. So let's identify our element. The atomic number will be 20, and so this will be a calcium nucleus. And so this kind of gives you the power to predict, what new nuclei will be generated, what type of radiation will be given off, so on and so forth. So go ahead and try those last 3 problems right quick for us. Check yourself with the key, and then you are good to go. So thanks so much, guys. I enjoyed covering this topic with you. I definitely had to do a good bit of study to put this together, but that's always good for me. And so I hope y'all have a great day.